So this presentation is the work of myself and my supervisors, Ernst Rank, Viktor Krahle, and Stefan Kollmannsberger. And it's also partially financed by the German Research Foundation. So before jumping into it, I would like to give you just a short introduction of, or like an idea of the presentation. So we have been talking about simulating the heat evolution in SLM processes over the last days. And I think the common agreement is that we need some sort of local refinement. And HP finite elements have been really successful in dealing with those, well, with the multi-scale nature that we have in space. But one of the issues that we still have is that in time, it's the same thing, right? So it's not only multi-scale nature in space, but also in time. And the idea of this work is that we kind of consider this combined space-time domain, and then we don't do a time stepping, but we discretize this with space-time finite elements, and that would allow us to basically choose an adaptive method that doesn't only refine in space, but in this combined space-time domain. Now, to recover the video that I just showed, you would then have just a slice that sort of travels through this domain in time. Of course, solving the entire problem in one go isn't really attractive, because that would limit the kind of problems that we could compute. So we would still like to recover a stepwise solution, or as we call it, a slab-wise solution, where we basically choose parts of the entire time domain, and we basically progress also in steps that are conforming to the elements of the base mesh here. And then the idea is that as opposed to time stepping, we can really choose also the problem size. So if we are simulating on a laptop, for example, we could choose very small time slabs that are still refined locally in space-time. But if we think of really utilizing HPC resources, then we could also go for very large time steps. That would then be very expensive to solve, but also give us the solution of maybe even many laser strokes. So my talk is structured as follows. So I will introduce the model that we are using, then I will talk about the formulation, and I will try to give you an idea of how we define these HP basis functions in 4D, which is eventually the goal. And this is, of course, requires some structure. So we use the nonlinear heat equation with phase change. So we have also a volumetric source here that basically has an extension in the z direction. This is a parameter that we can choose and then kind of fit to the measurements. The phase change model adds this latent heat term here, which is then expressed in terms of this smooth phase change function. And this gives us this peak in the heat capacity. And on top of that, we also add a little bit of conductivity in the liquid phase, which allows us to dissipate the heat a little bit faster, which is mainly there to tune the length of the melt pool. It doesn't really have too much influence on the other parts. The depth of the melt pool is influenced by how we choose the Z extent of the source. And then the entire cross-section area, you could say, is then determined by the absorptivity that we choose. The weak form is then a Petrov-Galerkin formulation, where we want to find a solution from H1. But instead of testing with the standard functions from H1 as well, we test with the time derivative of those. And you can really see the connection here to also convection dominated flow, where you then have these streamline upwind methods, which in our case is a bit easier because it's a pure transport in time, and it's really orthogonal to the space direction. And then you have only diffusion in space, but you don't have diffusion in the time direction. So this simplifies things here a bit. This is a not so new approach that you can check out here. The discrete weak residual and the linearization is then the following here. And you can also see that we have the time derivative on the test functions here. This gives us this mixed term between temporal derivative, so time derivative and spatial gradient. But by the way that through the way that we choose our meshes and the way that they're orthogonal between space and time, it doesn't really pose any challenge really. Then to make the nonlinear iterations converge nicely, we have to make sure that we integrate the elements that contribute to the phase change accurate enough. And because the nonlinearities introduced are pretty tough, we also use a bisection type algorithm that helps us to obtain an improved update as opposed to always following the entire Newton update. This is especially important as with this space-time approach, you don't really have a nice initial guess. So with the time stepping, you can also always use the previous solution as a kind of initial guess. But here the previous slab really just serves the initial condition, which is a Dirichlet boundary condition for the next slab. And that doesn't really explain, or that doesn't really give us anything or any information how this then extends into the domain. So something that we also do to make this a bit nicer is that we start with a very smooth phase change that helps us to obtain a good initial guess before we then make or set this parameter to whatever we want. So then the real challenge is to define these HP basis functions in 4 dimensions, or in general in more than 3 dimensions really. And we do that by first starting from a base mesh, and then we have a space tree based refinement. So in 2D here it would be a quad tree. So we query a refinement strategy that gives us then some cells that we want to refine, and then we do this recursively until we don't have any elements to refine anymore. Then we select some polynomial degrees. So in this example here, I choose polynomial degree 3, 2, and 1, which is really just for the example. So there's no restrictions with respect to the polynomial degrees. They can differ between elements. They can be anisotropic and so on. In the hierarchical view, we would have something like this. And this leaves us now with the problem of hanging nodes. So you can see here that there are some nodes that are not really compatible, or some edges. And this then translated looks like this. So we have shape functions here that then we would like to complete with something like that. But instead we have these shape functions, and then the question is how do we find a combination that then adds up to that, and especially then how do we do that in 4D? And yeah, so the idea of this multi-level HP approach is to go a different route and realize that we have a hierarchy in our grid, and that we can really just complete this shape function on that side without really bothering with these overlay elements. And of course, as you can see, there's a difference in the support. So you have a slightly larger support here, but this is just a trade-off, and this price is something that we have to pay with that method. Now, one thing that we have to make sure is that on these overlays here, we don't have any active shape functions. So that, because otherwise there's nothing on this side that we have to complete those. So that's the only constraint that we have to satisfy. And in order to do that, we distinguish between external boundaries. So these are cell faces that coincide with the domain boundary. And on the other side, internal boundaries, which are cell faces that are not part of the external boundary, and they are also not interfacing to another cell of the same level. So it's different levels. And then we have cell interfaces, which are just cells, interfaces between 2 cells of the same level. So this then allows us to construct a multi-level HP basis with the goals that, first of all, we want completeness. So each leaf should be able to represent polynomials according to whatever we chose. We want to have continuity. So no overlay basis functions. So translated to our setting, that means that no overlay basis functions shall be active on these internal boundaries. So the blue lines from the previous slide. And we also need to be a bit careful with what shape functions we introduce in order to not introduce any linear dependence between those levels. And the basis for the algorithm that I will just quickly show in the next slides is that we use d-dimensional arrays of Boolean values that we call tensor product mask to track active shape functions. So that then looks like this. So we have in this example 2 cells, and we have this this tensor product mask, which in 2D is really just a matrix basically that tells us in the tensor product of our shape functions which are active and which are not active. And clearly in this case, we can see that we are not having a compatible set of shape functions. So there's no way that we can combine them to something that is continuous. And in order to do that, we have 2 operations that restore that. So we have an operation that takes these 2 slices and activates shape functions if they are active on one of the 2 sides. So this is what you could also say it's a Boolean or logical OR operation on these 2 slices. And on the other side, we have something that deactivates if a shape function on one side is not active. So this would then be a logical AND operation. And this is really the core idea of what I'm presenting, that we have algorithms that work in terms of the interfaces between cells and nothing else. So we don't really consider anything else. We just try to formulate our algorithms in terms of these, because that allows us to extend those algorithms to really any dimension, because it's not really hard to do in 4D or in really any dimension. So I would quickly like to show the algorithm just to show you that it's really no magic and it's a pretty simple idea. So the algorithm is that in the first step, we activate all the shape functions on our leaves of the refinement tree. So that will give us something like this. So we have polynomial degree 3, 2, and 1. And on the others, nothing is active. And this leaves us with a state of non-compatible shape functions here. So in the step 2, we use this OR operation to activate shape functions on these non-leaf cells. And as you can see here, that there's one contribution missing from this cell that should contribute to this nodal mode. So we have these 3 contributions, but it doesn't, it's not completed by this cell. So we have to basically follow this with another iteration of this algorithm to then communicate the information from here, not only to these 2 elements, but also one distance further. Then step 3 is that we deactivate everything on internal boundaries. As you remember, we have these internal boundaries here, and we simply deactivate everything. And we have a similar scenario that there's one shape function here that still contributes to this nodal mode, which should have been deactivated. And therefore, we follow by another step that's very similar to the second iteration, now just with a Boolean AND, and this will deactivate that shape function. And that's basically it. I guess this is the core of the algorithm. And what you see here is the state of what shape functions are active and what shape functions are not active. And the principle is the same for 2D as it is for 4D. Now there's another step that I don't really go into much detail, but it follows a similar idea that then constructs the global indices and leaves us with just a numbering where we can see, for example, here that this nodal mode has contributions from all these 4 cells as we would expect. And then the location maps for the individual elements would be the active shape functions plus all the parents. So we then take these 2 active shape functions and we append all the parents. And that will give us the location map for this element. And as you can see, There are slightly more than the 4 shape functions that we would expect, so there's a price also here to pay. But as I said, it's the focus here is for now on simplicity. So this is really the core of the method. Now I would like to show how this looks when we actually apply it to some examples. So we computed this AM 2018 benchmark. The setup is according to the specifications. It's a 3D example. So now, of course, we are computing in 4 dimensions. The absorptivity is 0.32. Then this source depth is 0.3 times the width. And the phase change is a little bit smoother than with it would be with 1.0, and we also have a little bit of added conductivity there. The discretization is 12 by 12 and 2 elements in Z and 8 elements in time, and that will allow us to compute this problem in 8 nonlinear computations. We also have 5 levels of refinement. We have p equals 4 in space, p equals 1 in time, which is really for now just a choice that I made. It doesn't really mean that this is optimal, but clearly we also need some form of error estimation in the future. And this gives us around 60,000 unknowns per computation, so per one of these 8 slabs. Then in the computation, we see these are now 3D slices through time. And you can see that the refinement here follows the path of the laser pretty nicely. You can also see in which slab we are here. So it's 8 computations, as I said. And if we look at the geometry of the melt pool, then we can see that the tuning of the parameters was reasonably successful. So we get a very good comparisons to the experiment in the melt pool dimensions. For some reason, the cooling rate here wasn't really very nice. I don't really know what the reason for this is. Definitely needs some further investigation. And then to show that we can also do like more realistic or more expensive computations, we basically take exactly the same setup and we just let the laser not run once from right to left, but basically have the square and then hatch the area inside. That if you look at this, we also see that here the refinement tracks the laser very nicely. We can also see that now we have more slabs than the 8 that we had before, but it's still not as, like, we don't progress as fast as we would with a time-stepping scheme. We also see that we still have a very good estimate of this melt pool here. Because this video takes a long time, I think this is gives a better impression. So this is in real time now. It's about 6 seconds of simulation time, and it's about 3.4 meters of laser distance covered. And the computation was done on a single CPU. And as I mentioned already, the idea is that we move this entire setup then to something that works on HPC systems in order to bring down the computation time, which was a few days for this. Now, if we zoom into the very final bit here, then we see that we can also extract some information about the melt pool here. So as we expect, the geometry of this melt pool changes and it becomes bigger towards this end where the tracks are in very close distance temporarily. And yeah, so we just can look at the melt pool geometry here. And for example, here it's 60 micrometers, the depth, as opposed to the 37 that we had for this AM benchmark. All right, so with this, I would like to conclude. So we introduced an efficient alternative to the multi-level HP approach, which was introduced a couple of years ago for 2D and 3D. That in our case extends well to really any dimensions. We show that this enables us to do local refinement in in this combined space-time dimension, not only with adaptive time stepping, but really with different accuracy in time depending on the spatial location. It allows us to exploit HP capabilities. We also can use what we call the trunk space, which then would be reducing some of the modes from the tensor product that are not required for convergence. We use a simple phase change model that doesn't have any directional dependence on the laser travel direction. And we already get a very competitive performance on a single CPU. And as I said, the idea is then to extend this to distributed memory parallelization and HPC systems. For that, we need to investigate linear solvers and preconditioners. So I think this is a very important topic that will really decide whether this makes sense or not, I would say. We also want to extend the physics. So we want to simulate with actual metal power layers. And that together also then needs some further model validation. So these were my references. And with this, I'd like to conclude, and I'm happy to answer any questions.
Thank you, Philipp. Surprisingly, I don't have any questions.
Who would have thought?
But maybe the audience does. So
I can say maybe something.
Yeah, sure. Go ahead. You have 10 minutes. No, 5, 7.
So the code is partially open source. So this entire refinement that I introduced here is all open source. The space-time stuff, which is really related only to the model and some very specific things, is not yet open source because it's also a bit of a mess and not entirely published. But if anyone has any interest in the future, you can just let us know.
There is one from Vamen Sivat from the audience. I'll read it out. Thanks a lot for this amazing talk. We should use more deep math techniques to improve our simulations. I would be interested in your opinion about combining your approach of discretizing space and time with HPFEM with a real error estimator.
Absolutely,
space and time.
Absolutely. I think that's even necessary because so the refinement that we have here, I think you can see it, right? It's just not in full screen. So that was already not very trivial to come up with. So this is basically hand-tuned based on the history of the laser. And it doesn't really, I mean, it captures it pretty nicely, but it also it does use resources in places where you don't really need resources. And then sometimes it also misses some things. So I absolutely agree that we should use more error estimation. And I also think that this whole topic of DG-FEM with space-time might also be something that is really interesting to look into.
Then the second part is, do such error estimators already exist?
To be honest, I don't know. I mean, error estimation is a big research area, of course. I'm sure that there exists some. I don't know if there is something that would be directly applicable to what we are doing.
The principal theory exists, and I think that it would be, we would have to look at it. Massimo, please go ahead with your question.
Hi, Philip.
Hey.
Thank you. Very nice talk, by the way. And yeah, what I want to ask is, which is the ansatz order that you use for this large simulation?
For this one here?
Yeah.
So it's p equals 4 on all the levels except for the finest 2, so on 0, 1, 2, and 3, and then p equals 3 on levels 4 and 5.
Ah, okay. So it's adapted also in this sense.
Yeah, it's but only in space. In time, it's for now p equals 1. And also if you look very closely here, you also see that it's not perfectly resolved. So if you really look closely, then you see
the spatial resolution looks very fine compared to the melt pool size. You have already like 2 or 3 elements for the melt pool width.
Yeah.
You think maybe have you tried with linear elements everywhere?
In time?
Or like,
what?
no, in space. So p equal 1 or p, like lower order, because now you are using.
Maybe, but also the problem with how this multi-level HP method works is that you have a lot of overlay shape functions coming from here. So it tends to be more efficient to really go for higher order here. So I think if anything, then I would remove one level of refinement.
Yeah, but far away from the mel pool, okay. But since you are already refining a lot around the mel pool, you are still keeping, you said p equal 4, no, p equal 3.
Yeah, on these two levels here, yeah.
I don't know, but maybe that can help to slow down a little bit the computational time. Anyway, the result in quality of the approximation that you get are really impressive. And I think for the cooling rate, maybe it's because the uncertainty they have on the measurements are pretty high.
Yeah, I was also thinking that, but I was a bit scared to doubt the measurements. So I don't know.
Yeah, but they have a uncertainty quite high on the cooling rate. So maybe that's the reason.
Yeah, I saw that you also overestimated it. So I was a bit more confident that maybe it's not so bad.
Exactly. Thank you anyway.
Cool, thanks.
Yeah, in this sense, I'd like to quote Sohayoshi Basho said, everyone believes the results of the experiments, but the one who did the experiments, and no one believes the results of the computation except the one who did the computation. I mean, the real hope here is to be able to solve parallel in time.
Yeah.
What do you think?
So I think that we had this discussion about the aspect ratio on one of the other days, and someone mentioned 10 to the power of 8, and right now we are away by a factor of around 4,000 from that. And this doesn't really seem that far out of reach if we think of doing this in a parallel fashion, maybe also with a bit more efficiency. So that's definitely the hope, that we can do this in parallel.